So today I will present the solution to problem D in BGOpen 2018. The problem is dice and ladders. So in this problem, as input, you are given a board of the game ladder game, the children's game, and a probability P. So the ladder game is a game where you roll your dice, and then you move like for example, I'm at cell 1 and I roll my dice and I get the number 3. Then I move 3 steps, 1, 2, 3, and I end up at cell 4. But cell 4 has a ladder at it. So then I will continue to the ladder and I will get at cell 7. So the problem is, given the probability P, how many dice rolls are required so that you will, after the X dice rolls, finish the game with a probability greater than P. So in order to solve this problem, we need to do some observations. So the first observation is that this problem has the properties of binary search. So that if I know that if I, after X dice rolls, will finish with a probability greater than P, then I know that will also be the case for X plus 1 dice rolls. However, if I know that for X dice rolls, I will not be able to finish the game with a probability of P, then I know that the same will also be true for X minus 1 dice rolls. So this means that we can do a binary search for the number of dice rolls required. But how do we find the probability of finishing with a certain number of dice rolls? So let's have, if we ignore the ladders for a second, and we have a look at the board the way it is, we know that if we are at cell 1 and we throw a dice, then the values of the dice can be either 1, 2, 3, 4, 5, or 6. So then there is a 1/6 probability of moving 1 step, 1/6 of moving 2 steps. So we can see if we are at cell 1, then we can only move to the cells 2, 3, 4, 5, 6, and in fact 7, and all with the probability of 1/6. So, but what if I do, so this is starting at 1 and doing a single dice roll. But what if I do multiple dice rolls? Well, we can actually construct a full graph out of this. So this is from all the outgoing edges from node 1, and we can do the same for node 2, 3, 4, 5, 6, and 7. And then we can look, starting at, for example, node 1, what are all the possible ways to move to, for example, node 4 in less than in crossing two or less edges, or fewer edges, and then or crossing exactly 2 edges, and then so if I go from 2 to 3, so the probability of me going from 1 to 3 in exactly 2 dice rolls would be 1/6 times 1/6. So in fact, we can construct a large graph like this, and this we can observe that doing this combination of the graph is actually the same as a matrix multiplication. So let's construct a matrix for sample input, ignoring the ladders. So in this case, we will then have a 9 by 9 matrix. So we have 1, 2, Okay. Alright, we have our matrix. Okay, so here is our matrix. So let's start filling it out. So when we start at node 1, the probability of moving to node 1 is cell 1 is 0, since we cannot throw a 0 with our dice. While the probability of moving to cell 2 is 1 over 6. The same with 3. And up to 7. However, since we cannot throw 7 or more with our dice, the probability of going to cell 8 and 9 are both 0. And so we can do the same for cell 2. So since we cannot have negative numbers on our dice, the probability of going back to cell 1 is 0. And the same is for standing still. And then we have it's the same as with the last one. And as the same as from cell 1, we cannot move to cell 9. So the probability here is also 0. And you can continue filling out. And so this is an interesting case, because if we're at 4 and we throw the number 5 with our dice, then we'll end up at cell 9. But what if we throw the number 6? Then we'll get past cell 9. However, in this problem, we say that when we pass, we also finish. So then we say that the probability of going from cell 4 to cell 9 is actually 1 over 3, or 2 times 1 over 6. And so we can continue filling out. So now we have filled out our matrix. We can use it to calculate the probability of moving from one cell to another in multiple dice rolls. So, say we are at cell 1. And we want to find the probability of moving to cell 4 using exactly 2 dice rolls. So, and we can simplify this because we know that we will never, we will never need to move to any cell past 4 because it's impossible to go back. And so we only need to look at this submatrix here. So okay, we see the probability of moving from 1 to 2 on the first throw is 1/6, and the probability of moving from 1 to 3 on the first throw is 1/6, and from 1/4 it's also 1/6, but we know that on the second dice roll we'll have to go past cell 4. So actually the only 2 intermediate cells we can have is 2 and 3. And going from these and back to 4 is has probability 1/6 each. And then we can see, okay, so taking the route via 2, we get probability 1/6 times 1/6, and same going via 3. So in fact, the total probability of going from cell 1 to cell 4 using exactly 2 dice rolls is 2 times 1/6 squared, which is 1/18, I believe. Yes. So the answer in this case is 1/18. And so, what if we have our ladders? So in the sample input, we had a ladder from 2 to 3 and from 4 to 7. And what we simply do in that case is we look up the position. Okay, going from 2 to 3 is 1/6. But since we will, in that case, we will sorry. So anytime you hit node 2, right, you will automatically follow the ladder to cell 3. So we see that so the only way we can hit node 2 is from node 1, and so the probability of arriving at node 2 from cell 1 is in fact 0, and we can add this previous probability to the probability of going from 1 to 3, so we now get 2/6, or in fact 1/3. And then we can do the same for the second ladder. So we see that, okay, all of these are probabilities of going from these cells to cell 4. However, since we will automatically follow the ladder to cell 7, we can remove these, and they will all become 0. And then we can all add those here, so we get 1/3 for each of these. All right. And now we can use this matrix to calculate how the probability of moving from one cell to another in multiple dice rolls. Because in fact, the probability of moving from, for example, cell 1 to cell 9 using one dice roll is 0. But if we want to do it with 2 dice rolls, we simply do a matrix multiplication. Because in matrix multiplication can intuitively be viewed as trying all possible intermediate values and summing them up, right? So we try, okay, going via 2, going via 3, via 4, via 5, via 6, via 7, via 8, and we multiply the two probabilities and sum all of them together. And so by multiplying this matrix with itself once, we will find the probability of going from any cell to any other cell using exactly 2 dice rolls. And we can do this for as many dice rolls as you want using matrix exponentiation. So in this case, we can use so that in order to find the probability of going from cell 0 to the last cell, which we will call T in this case, is in say X dice rolls is m to the x, where m is this matrix which we have now constructed based on our sample input. So it's m to the x, and then we look at from 0 to t. And so we only need to do the matrix exponentiation in our step for each step in our binary search, and check if this is greater or equal to p. However, if you do this naively by simply doing an iterative matrix multiplication, this will be too slow, since we know that we can from the problem statement, we know that this number may be 10 to the 9 or 1 billion. So what we do is we utilize the nice identity that a to the b is also equal to a to b over 2 to the second, and we can create we can use this so that, okay, since calculating a to the b is very slow, but calculating a to the b divided by 2 is much faster, and we only need to do this one, and then we multiply this by itself. And then we do this iteratively, and we will get a very nice and fast matrix exponentiation, which and our final solution comes out at O R times C, where R is the number of rows and C is the number of columns, to the third, since matrix multiplication, it has complexity n to the third, and times log squared of x, where x is the size of the answer, which can at maximum be 10 to the 9.